Hi, today's video is about dipole moment and you'll be learning what they are, what are the nuances that they have, and what is the real significance, that is the physical world significance around us because of these dipole moments. So I'm Atray and I'm the HOD of Physics and Chemistry at Cosmic Essence Education, and I'll be teaching you dipole moment today. So let's start. So first things first, we'll first discuss what is a dipole and why is it so important. So dipole is a name given to a system of charges such that one charge is plus q and another charge is minus q. That means their magnitudes are the same but they are of opposite signs and the distance between them is fixed, say 2a, right? Why are we writing it as 2a? Because from the midpoint of both of these charges, from the midpoint the distance is equal. So in total we are saying that the distance is about 2a, right? Again, this is what this system is, what we call a dipole. Okay, not a single charge, not any distance, but a fixed distance between these charges. Now why is it important? Because although this system of charges is zero in total charge, that means there is no total charge in it because they are cancelling each other out, but the electric field by this system is not zero. It is actually different at different points. That means at the equatorial plane, which is the plane perpendicular to the dipole, equatorial plane as well as the axis, dipole axis plane, the electric field changes at different points. We can also find electric field at different points in the other planes as well, but it is difficult to find, so we won't be talking about them today. Now, usually we denote a dipole by the symbol P, right? We denote it by symbol P, and a dipole is also given a direction, and the direction is given from direction of P, that is direction of the dipole is given from minus q to plus q. That means this will be the direction of the dipole, of this dipole that I have made, right? Now this is the convention that we are using. That means that these are the set of rules that we have defined as scientist community to figure this out, that this is what we'll call a dipole and this is how the direction of a dipole will be decided, right? So that is very important to understand. Now once we know this, let's now figure out the electric field by a dipole at different points. First we'll be talking about on its axis. The axis is essentially this. So suppose this is my dipole, the distance is of course 2a, and from the center point I take a point x such that from the center point the distance of x is r from the center point. Okay, remember I am taking r from the center. Now as soon as I take this, I need to find out the electric field over here, and the electric field over here will be given by superposition law. That means the electric field by this charge and the electric field by this charge will be added. So the total electric field that I am looking forward is just a sum of electric field by plus q and electric field by minus q. What will be the electric field of plus q? It will essentially be k q upon, now what is the distance? Distance is essentially a, this is the distance a plus r, so this becomes r plus a whole square, right? Because this is the distance of x from plus q charge. At the same time, here it will be r minus a because the same distance is there, but now here I will be using minus q charge, so it becomes a negative thing, right? So now I just have to simplify this quickly. I'll do it over here. So when I simplify it, it comes out as minus q. I will have to take kq common. As I take kq common, now r square minus k, this becomes 4qa on the numerator, and below it will become r minus a into r plus a full square, right? That means this will become r square minus a square, r square minus a square full, sorry, here it will be r, my bad, this will be r, not q. So this is my final result for E. Final result for E. Now, what happens if my A is very small than R? That means R, that is this X, is very far away from the dipole. What can happen then? If R is greater than equal to A, then what happens is I can almost forget about this A square because it will only get smaller. So I can put my electric field as K into Q 4RA upon R cube. I can just write this as R cube because I can remove this. So it becomes 4QA into K upon R cube, right? So that is the electric field on its axis by a dipole, okay, and this is on the axis of the dipole itself. Now, which is the direction? What direction is this electric field in? How will I figure out the direction? Direction is given simply by the pull, right? So the direction is essentially in the same as dipole moment. It is the same as dipole moment, which is this direction. So here the direction is same. The sign of electric field will give me the direction of dipole moment. Alright, so that is about dipole moment, the electric field by the dipole moment on its own axis. Now, similarly, I can also find the dipole moment electric field on the equatorial plane. It has simple, right? Again, I'll take my dipole plus q minus q, obviously this is 2a, and this is my equatorial plane which is perpendicular to the dipole plane. Let's say I take my x over here, right? If I take my x over here, now I need to see what is the force. From here the force will be this way because it will repel, and from here the force will be this way, it will attract. That means this is how they'll connect, and I will also have an angle, say theta over here from the dipole axis. So this is theta, this is that. Now when I have two vectors like this, what is going to happen? The vertical components will cancel out. Why will they cancel out? Because the distance of this point from both of these charges is the same. This distance is equal in both of them. How? This distance is A, this distance is A, and this distance is R, right? Because we take the distance of the point from the center of the dipole. So this distance is R. That means this distance is R square plus A square, root of R square plus A square, right? That is how we figure it out. This is simple Pythagoras theorem applied over here. This is also R square plus A square root, as well as this is also the same. So both of these will have the same magnitude, and the vertical components will cancel out, and the only remaining component will be the horizontal component, like this. And as you can see, the horizontal component is opposite to the dipole moment direction. It is opposite to the direction of dipole moment. Let's figure out what is the magnitude of this. To find out the magnitude, again we will just have to add the cos theta. Why cos theta? Because this is theta, so the magnitude over here, E of plus Q, which is equals to KQ upon R square plus A square. This will be the electric field over here, and I will just have to take the cos theta over here, and then I will be adding both of them up. So E total over here is 2KQ upon R square plus A square cos theta. Right? So this is how we figure both of these things out. Now, what happens if, okay, maybe I think I've done some mistake somewhere. 2KQ, I will have to add both of them, cos theta. Yes, I will put up, what I'm going to do is, I will also put the value of cos theta over here. What is the value of cos theta? Let's look from this triangle. In this triangle, this is A, this is R, this is R square plus A square root, and this is R, right? So cos theta is simply the base upon hypotenuse, base upon hypotenuse. So base here is A, and hypotenuse is root of this. So my cos theta will come out as, since cos theta is equals to A upon R square plus A square root. This is what cos theta is. This is the definition of cos theta. I will put that in the electric field. So I will put it up, and 2KQ upon, this will become R square plus A square 3 by 2, and on top I will be multiplying with an A, and this is my final result of the electric field at this point, right, X. Now what happens when R is greater than A? That means this is negligible. As soon as it becomes negligible, what's gonna happen? I can neglect it completely. I cannot neglect the A in the numerator, remember, okay? Just because it is getting added up, so I can remove it. Why can I remove it? Let's quickly understand. The neglection is essentially because it's so small that imagine a big number, right? Say I have 1 lakh rupees, right, or 1 million dollars. If I'm adding $10 to $1 million, there's not a big change. So it's almost like I can remove that $10 and I can still keep the $1 million, and I'll still nothing would change for me, right? That is exactly what we're doing here. For a big number, an addition of a very small number does not change much. So I'm completely removing it and neglecting it, and I'm only keeping this. But multiplying with that number makes a difference, so I cannot remove that. So as soon as I do this, this gets cancelled out, this becomes R cube, and I will get my electric field as 2KQA upon R cube. And this becomes my electric field at this point on the equatorial plane, right? Now, both of these are very important to understand and very simple to grasp. But why is this so important? Why is dipole moment so important, or what is the physical significance of it? The physical significance is that when we are dealing with molecules, right, especially in chemistry, when we are dealing with molecules, there are molecules like H2O, which is just water. H2O has a permanent dipole. That means it has a dipole moment which always is there. That means there is always a directional charge between the molecules. Now what happens is, when I put an electric field, pass through an electric field from water, those dipoles are gonna transform and they will have an effect, and that will to figure out what effect the electric field will have, I need to understand the dipole moment of H2O. At the same time, dipole moment of H2O is also the one which attracts other ions and other elements in water, right? So all of that, dipole moment has a lot of importance in the chemical area because it's a very tiny space. Now the important thing to remember in the electric fields that we did was, one, dipole moment reduces by a factor of r cube. Usually in Coulomb law, the electric field reduces by r square, that is, the electric field is inversely proportional to r square, but here the electric field reduces by a power of r cube. So that is a very exponential decrease in the electric field. Second, in the case of dipole, where I am reducing the dipole that means I am reducing the distance between the charges, and I am increasing the distance between the external charge, that means the test charge that I want. The formulae that we have figured out for after neglecting A are exact. They remain the same, they are exact because it works very well. Okay, we call it a point dipole. So for point dipole, those are exact formulae. Okay, so that is all about dipoles. I hope you understood it really well, and let me know in the comments if you have any questions about dipoles. That's it. Thank you for watching that video, and I hope you understood the concept of dipole really well. If you have any questions whatsoever, and if you want to give me a suggestion of as to what topic I should be choosing to make a video next on, then reply below in the comments and put it down in the comments, and I will definitely have a look and make up that video as soon as possible, or answer that query as soon as possible. Do not forget to like, subscribe, and put that bell icon on so that you are notified as soon as we put up our next videos, right? So